take the other students around owing to the fact that they may not be able to come up with. So I'm taking with you exclusively these questions. They are of Olympiad level. We need to seek the understanding of concepts through these questions.
So your voice is pulsing. Not able to hear you very clearly.
Okay, we will try to understand a few concepts
Yes, sir.
vis-a-vis the questions which we are to solve this day on the topic current electricity.
Yes,
Am
sir.
I audible?
So faintly.
Faintly audible. Okay, we'll try to screech then. We will not be in a position to disturb the arrangement owing to what I'm carrying as a baggage of my experience yesterday. So let the device be at its place. Let the sleeping dogs lie. Let's get started with whatever possible in my capacity. I'm studying my vocal cord here. Now, Vasudev, there is an understanding on Gauss's theorem. We are aware of it,
Yeah.
right? We're aware of Gauss's theorem to be precise. Frederick Gauss is what the name being, right?
Yes, sir.
So, what I'm to ask you is, can you change the articulation, the formulation? Why I seek change? I'll be using these later. There are many a place where I'll seek change in presentation of formulae. First being the Gausses. There are two syllables, please be very careful. Gauss is what it's called, right? Okay. So if it's about English, then there are two syllables over here. One is Gau and the other is S. So the correct pronunciation is Gauss, two syllables.
Yes, sir.
Okay. If that's an issue, then we can go with his name. He was a German physicist and mathematician. So the name has also got Frederick as the precursor. You can add. Let be what it used to be. So Gauss is what I'm taking over here, and Gauss, we are just a minute. Let me accept the call. Difficult. Okay, is it on?
Yes, sir.
Recording on, right?
But so your voice has degraded.
For the duration. Satyam, come over here. Get the number. I'll ask him to add. Get your number. Write down the ball. Right there, please. Come in. So you we have to take different form of Gauss, and a different form of Gauss being E dot ds is equal to q by epsilon naught known to us, correct? E dot ds is equal to q by epsilon naught. Would you please mind adding this number? Also, Dave,
Okay, sir.
take the different device.
Invite
E dot
participants.
99802. Is it visible?
Yes, sir, it is. Let me just try to add. Seven five. Oh, it's 975. Is it okay?
99802 is 575975.
Um, Yes, so the search results are not turning up anything.
99802-75975.
Yes, that exact number. I'm not getting anybody I can add for that. It says this number doesn't represent any type count.
Okay. Let me then. Let's go ahead. We write the Gauss's form there. What is that to us? Doctor, we can come over here and note it down. The number is not operational. Come over here. Here only you can take. Physically. Okay. E dot ds is what to us? Is equal to q enclosed. We are aware of it. Q enclosed by epsilon naught, right? Yeah.
Yes, sir.
E dot ds is equal to q enclosed by epsilon naught. This being known to us. And what do we have? What's the problem? And what do we have is from here to get another form, which I'll be using in current electricity to solve a few questions. Those questions are to get us insight on the understanding vis-a-vis concepts. If you want to write it down in the other form, I want to incorporate sigma here. If I want to incorporate sigma, and EA is what I write for, assuming it to be constant through and through. What we get from here is EA, the area over which it is being integrated, E being constant over that area. So EA is equal to Q enclosed by epsilon naught. E into epsilon naught over here will therefore be Q enclosed by area, which is nothing but sigma. Right?
Sir, but
Yeah.
Q enclosed is any charge that's inside the Gaussian surface. How do we know the charge is on the surface?
No, I didn't say charging on surface. It's charge inside.
So then what does Q in by A represent?
Yeah, I got your point. I got your point. When I'm writing over here E dot ds, right?
Yes, sir.
And I'm referring to a shell.
Oh,
Okay, there's a shell.
Yes.
The charge enclosed, it is Q in, which is what is Q to us. Sigma of that shell. Got it?
Yes, sir.
What do we get from here? E into epsilon naught is equal to what to us? Is equal to sigma to us. Correct?
Yes, sir. So there's a shell and a Gaussian surface is like just outside the shell. I mean, a shell encompassing a shell.
That
Okay.
that is right.
Yes, sir.
Got it?
Yes.
Okay. Now this is an equation which I'll be using. This is the point form of Gauss's theorem. We can mark it as point form of Gauss's theorem.
Yes.
And E we are aware of. We are not greenhorn to this E. We have gotten this E earlier as well. E is what over here? Sigma by epsilon naught, right? What is E over here? Sigma by epsilon naught. That is what we are getting over here.
Yes, sir.
Now there are a few terms which I wish you to mark. There are a few terms which I wish to mark, and that will be vis-a-vis curl, delta. We are aware of Maxwell's equation. I'll be using one of the 4 Maxwell's equation which we are to make ourselves acquainted to vis-a-vis IIT preparatory course. I'm using one of the 4 Maxwell's equation, and that is what to us? I presume gradient must not have lost on you. Gradient, I use the term gradient or grad,
Yes, sir.
inverted triangle, right? So I'm going by the gradient uses. What I'll do over here is, I'll take dot product of the gradient with epsilon naught and E. I repeat, I'll take dot product of gradient with epsilon naught and E.
So gradient of what? Potential?
Gradient of a term, which is what will be not named in the class. That's the reason I said that it's the dot product of gradient with epsilon naught and E. Epsilon naught is a constant. E is electric field, and gradient 2 is vector in quantity. So I can go ahead with the dot product of gradient with epsilon naught E, E vector. Got it? Collectively, what will it be called? Epsilon naught E will be collectively called D, D vector. Now, pre-barricading your interest on what D is, I'm not naming or mentioning it over here. If so falls the need, we'll go into the detailing of it. As of now, I'm not to dwell deep on that term. Why? Because I'll take my time off the other which I want to, and I want to get done with it. Okay? If possible, we'll certainly return. So what is capital D on face value? Capital D, a vector quantity, is nothing but epsilon naught into capital E. Okay? Capital D, a vector quantity, what is that to us? Epsilon naught into capital E. Got in India?
Yes.
What next I wish to? I want to find dot product of gradient with D, or dot product of gradient with epsilon naught E. Got it?
Yes, sir. But like the gradient of what? I think I already asked this question. Like, what quantity are we taking the gradient of?
We can find gradient of a scalar quantity.
Yes, sir. But what is this mystery scalar
It
quantity?
used to get us a vector quantity, correct?
Yes, sir.
The gradient of what over here? Gradient of what can be related to flux, dear?
Potential. Okay, wait. But then, E is defined as the negative gradient of potential.
When we are referring to flux, we are bringing in field lines.
Okay.
How it is entering. This is called divergence. You forced me to use the term. I didn't want to. But we are trying to figure over here, how are the lines diverging? It's a vector field. So the lines which are to manifest field, how are those lines converging, or how are those lines dispersing?
Okay.
You take a pillbox, lines are to enter, lines are to leave.
Yes, sir.
So how did they enter? How did they leave?
Okay.
We are referring to divergence. Diversity is being tested over here.
Yes,
What
sir.
India?
Okay.
So we are in a way relating to field, correct?
Yes, sir.
As we did relate to, do you remember I said curl of force? What did I take there? I wrote long back. Curl of force. What is that? Gradient cross F, correct?
So was this back in work, power, and energy?
Yeah, it was back in force.
Yes.
Conservation.
I think I might have
Conservative force.
forgotten about that.
Curl of force. And then I told you that if curl of force is 0, then force is conservative in nature.
Yes. Okay.
So there is equally of relevant a question, what is gradient? What are we taking gradient of? As we have asked over here, you would have posed a question over there as well, right? Yeah.
Yes.
So what would have been my answer to that question had been posed? The same. It's a vector quantity. We can find cross product of two vectors. We can find dot product of two vectors. When it comes to physicality there, what did I say? Basically what I'm testing on, how is force varying with x in solo, how is varying with y in solo, how is varying with z in solo. Is it varying or not? And if it is not varying, then that force is deemed to be conservative in nature. Doesn't depend. Doesn't depend on what x you are taking, what y you are taking, what z you are taking. It is zero, correct?
Yes.
On contrary, if it depends, then force will be non-conservative in nature. That is what we did extrapolate that equation to, correct?
Yes.
In exact similarity over here, I'm taking dot product of what? Two vectors. And what I'm to find over here is, how can the term which we are aware of be presented in gradient and E, capital E, right? You can come into gradient and capital E, correct?
Yes, sir.
We wish to find, we wish to get it. Okay?
Yes, sir.
So what do we have over here as per Maxwell is this term dot, you can write D to begin with, is equal to what to us? Rho by epsilon naught. Do check.
So rho is volumetric charge density.
Yes, it is volumetric charge density. Okay?
Yes, sir. So, but can't you simplify this because, well, D is a function of E,
Correct.
and well, E was defined as negative grad V, right? Yeah.
Correct.
So, and we are taking grad V dot D. So grad V
Mm.
is negative E. So can't we
Mm.
say this is negative E dot E epsilon naught?
You want to write in terms of E, it seems, right?
Yes, I mean, why introduce new quantity when you can do it in terms of one?
Yeah, we can. That definitely I was going to come to it. That I've told you already that what is D. D is epsilon naught E,
Yes.
right?
Mm-hmm.
D is epsilon naught E. You can write that down.
Yes, sir. I have already.
D is epsilon naught E. So what do we get from there? Basically, what you have asked me to do, what you have asked me to write, is what I'll be writing. I can remove this D from here without a introducing, without a much changes, because epsilon naught, they are all a constant. So we can mark over here, epsilon naught is taken down, so E, simply E will do.
Yes, sir. Wouldn't you get epsilon
Okay?
squared down
No. Because I'm taking it to be a constant. Epsilon naught, epsilon, they are different constants over here.
there? Okay.
If you're marking epsilon naught, then this will be the equation.
All right.
Basically, it is E is equal to what to us? Rho by epsilon naught. And then one more term. J. What is J? J is current density. What can we write? J equal to dear is equal to sigma into E. Tell me how.
So you derived this in like the first introductory class of current electricity.
Okay.
Uh,
So J is current per unit area.
yes, sir.
What is that to be marked?
Conductivity.
Sigma.
Yes.
You be very careful of the term sigma over here.
Yeah. It
It's
trips
not
up.
charge density. What
Yes.
is that?
Conductivity.
It is conductivity. This is conductivity.
Yes, sir. It says conductivity and conductance the same.
Yeah.
Okay.
You can mark it as resistivity here. You can mark it as resistivity if that is more for you to comfort. Okay.
Yes.
Now differentiate between this row and this row, please.
Yes, sir.
This row over here is resistivity.
Yes,
Make
sir.
that distinction.
Okay.
So J is what to us? J is E by resistivity. It is same as V equal to IR, isn't it?
Hmm.
R is equal to rho L by A.
Yes, sir.
It comes first. You can relate easily. Fine?
Yes, sir.
These two equations on board are to be used. We'll be using them.
So, could you again explain what the first of them physically represents?
Okay. What is the first one to represent?
Yeah.
What is it all about?
Yes.
It's about variation. It is about how is E varying. The variation of E on the surface. Which surface? Gaussian surface. If it's given to you in a region, what is rho? Let's say I give you an equation. So rho is varying as 5x squared.
Radially. Okay.
And then what I demask you is, no, radially, not radial,
Yes, sir.
any direction. X squared is varying with x.
Okay.
And then I ask you, if the field is conservative, can you get for that region Ex, Ey, Ez? Rho is given to you. How is rho varying in a region? It's varying with x, solo with x,
Yes, sir.
not with y, not with z. And then is asked, okay, tell me what is your take on Ex, Ey, Ez? You use this equation directly. You get from here what will be Ex. You get from this equation dEx by dx is equal to whatever rho given to you, correct?
So, what did you say?
From this equation, what you'll get is
Yes.
dEx by dx, because dy by dy will be 0, dz by dz will be 0. So this equation will boil down to dEx by dx, correct?
Okay, so wait, so we're applying the grad operator on the vector E.
Correct.
Okay, that's the confirmation I needed. Alright, I think you got the rest.
This is a dot product, right, dear?
Yes.
Need this application. The dot product. I'm not applying it directly to a scalar quantity. I think you're coming from there. That
Yes.
you're applying on a scalar quantity to get a vector quantity, correct?
Yes, sir.
That is, you want to write in that form, you can change it. But I'm finding over here the dot of two vectors. Which two vectors? Grad and E.
Yes, sir. Just a little bit of a technicality here. Um, People say grad is an operator. Then how can you define a dot product between something that's defined as an operator and a vector?
Operator means it is to operate on something.
Yeah. Okay.
Okay.
Yes.
So when I did introduce this term to you, what I tell you that grad is an operator. It operates on a scalar quantity, which will get me a vector. Right?
Yes, sir.
That doesn't take away from fact that grad itself is a vector quantity.
It is.
Yes, what did you write there that day?
Yep, sir.
d
That's
j I cap, d dy j cap, d d z k cap. Correct?
yes, sir. But you can't define that independently as a vector without something to operate on, right? I mean, k cap. This is just like an empty shell.
When you are direct into operation, right?
Yes, sir.
When you are directly applying it, for example, we applied it directly on a scalar quantity. Right? It's an operation, right?
Yes, sir.
then it is to do an operation. It is being directly applied on what? On a scalar quantity, which will get you a vector quantity. You are using it as an operation, a
Yes.
direct application.
Yes, sir.
Now coming to what exactly it is. What exactly it is. We have used it as curl as well. We have used it, if you are very much in your memory now, I have jogged your memory. We have used it as curl as well. So
Yes.
what was there it to be deemed? It was there deemed to be a vector quantity, as I am to operate cross product on a quantity which itself is an operator. Then there what is the operator is cross.
Yes, sir.
What is the operator there? Their operator is cross. What is the operator? Here. Their
Dot.
operator is dot.
Yes, sir.
And that was the reason I didn't want to dwell here. Why I didn't want to dwell? Because you are unaware of what is a vector field and what a scalar field. In time to come, I will boggle, I literally will confuse you with few questions. Once you are through magnetism, I'll ask you, what is magnetism? What is magnetic field? Is it a conservative field or is it a non-conservative field? It's a very difficult question to answer. Because what we study, you'll get to know B dot dl is equal to what? B dot dl is equal to mu naught I. So it's suggestive of B dot dl in a closed interval, mu naught I. What it suggests? It suggests that the field is what in nature? Is non-conservative in nature.
Yes, sir.
So what exactly it is? We get to know conservative or non-conservative. Provided we are aware of what is a vector field and what a scalar field. It depends on vector and scalar field. We cannot define them in isolation.
Yes.
So when I'm referring to over here as an operator, I'm applying directly on a scalar quantity to get me a vector quantity.
Yes.
Now, being a vector and we are in no odds with it, certainly it's a vector quantity. Vector will also operate on something, and that is what it is to do. It is operating there. When I'm saying curl of f, it is operating on force, correct?
Yes.
Similarly, when I'm saying dot with what? Dot with E, it is operating on what over here? It is operating on electric field over here. Got it here?
Yes.
So that will get me what? A question being asked. The questions are asked, by the way. Direct questions are asked for this. That will get me how E is varying with X. Accordingly, if rho is function of x, y, z, you know what to do. You'll get Ex, Ui, Ez in accordance, and can find E per se, E vector per se thereafter. So this is one of the four Maxwell's equation on board. And Maxwell equation is the set of Maxwell equation are the only which are to define whether a force or whether a field is conservative or not. Maxwell equation is to be laid credence to.
Yes.
And Maxwell equation will deal with gradient or grad. All the Maxwell equation will have this factor, gradient, grad.
Yes, sir.
Okay, dear? And we will not be treating there as an operator. We'll be treating there as a vector quantity. A vector which will operate on another vector in form of dot or cross. Got it, dear?
Yes, so this is just a different way to state Gauss's law, right?
One.
Yes.
The other way of writing, which according to us is of greater import than what we are aware or limiting or trying to limit ourselves to.
Yes.
There are questions on Olympiad. They will not be asking you on the organic form of Gauss's theorem. We'll be taking a few, but we'll ask you on the advanced form of Gauss's theorem.
So Could you give an example which uses that?
Yeah, we'll be taking the class person here, don't worry. V is equal to IR is what is being written in this form. J is equal to sigma into E, correct? Yeah.
Yes.
We're aware of Ohm's law. Now, Ohm's law cannot be validated for conductor. It can be validated only for point. You cannot define Ohm's law for a conductor. It will fail. But Ohm's law will not fail when you're defining for a point. So what is this, the one on board? It is point form of Ohm's law. J is equal to sigma into E. It is nothing but V is equal to IR. We'll prove that Ohm's law will not hold. That's the reason we have ohmic and non-ohmic conductors, correct?
Yes.
Ohm's law may not hold or will not hold for non-ohmic conductor, but point form of Ohm's law will hold even for non-ohmic conductor or the so-called non-ohmic conductor. For example, SCRs, they are non-ohmic conductors. You have a graph like this
Yes.
for V versus I. It's not a straight line, but for point, Ohm's law will still be validated. This is the more basic form of Ohm's law than what we study. V is equal to IR. What is it to us? J is equal to sigma into E.
Yes.
Idea? Now the uses, as you asked. What are the uses you ask, right there? I will factor in what you have studied and then we'll ask. Now we have been ranting on, if you can recollect, that whatever charge will come to the junction, it is to leave junction.
Yes, sir.
There cannot be any accumulation of charge at junction, because that is what KCL is based on. Algebraic sum at a junction. I presume you are aware of junction.
Yes.
More than 3 points, more than 2 meeting at a point. More than 2 branches meeting at a point. It's a junction, right?
Yes, sir.
3 branches at a point make a junction, correct?
Yes, sir.
Branches at a point make a junction. What is over here to be checked? Are we correct on understanding? Is it that no charge is present at junction? Is it that whatever charge will come to junction is bound to leave junction?
Yes, I mean, logically it has to.
If that's the case, then there should be no charge at the boundary of, then there should be no charge at the boundary of directives. Let's say I have a capacitor.
Yes, sir.
Let's say I have a capacitor. I have filled that capacitor with 2 dielectrics.
2.
Yeah.
Okay.
Okay. I have a capacitor. I have filled the capacitor with 2 dielectrics. This one. First one is K1 and second one is K2. Find out.
Yes, sir.
What do you say about this space? Will this space have charge or will be bereft of charge?
So, well, a dielectric in general does not have charge accumulation in any specific part of its bulk, does it? All it does have is polarized atoms, molecules.
So let us take polarization per se and ask ourselves, will there be any polarized charge over here on this space being 1 outwards? Will there be any polarized charge on the surface, or is it free of charge?
Actually, well, if you take any surface in any one of the dielectrics, if you consider all the molecules on that surface, the molecules to the left would be polarized rightwards. I'm assuming an electric field that goes this way, right, from K1 to K2. Then all the electrons would be pushed towards the left plate. But all
There will be dipoles. Dipoles are to realign.
yes, yes, all the dipoles would be pointing left. But then there would be a similar wall of atoms to its right. They would also be polarized to their right. So I think whatever electron density leaves to the left is replaced by the ones that are coming from the right to the left.
Are you asserting position on it?
Yes, that is if that plane we're considering is in the middle of one of the dielectrics. But if it is at their interface, then the electron density that's leaving there doesn't necessarily need to be equal to the electron density that's coming in from the other side. So
And how you are certain if it is symmetrically placed?
Sir?
How you are certain? How is it subject to placement?
Yes,
You made a
exactly.
statement it's symmetrically placed.
So symmetrically placed. I don't see any other way to place it. I mean, this is one dielectric, this is another dielectric right in the middle.
This can be thinner, this can be thicker in comparison. Then symmetry will not hold.
Sir, I don't think either one of them being thicker or thinner would affect the polarization at that point, because electric field.
What do you mean by symmetry? You use the term. That's the reason I'm asking. You coined the term symmetry.
So,
if it is symmetrically placed, means what?
So,
I
didn't use the word symmetry. You must have misheard me. I said since it is placed at the interface of the two dielectrics, the electron density that's being polarized this way in dielectric 1 might not be the same as the electron density that's coming in from dielectric 2. There would be a differential there, and that might lead to a charge buildup at that interface.
Okay. So if that's the case, dielectric is what you are proposing your argument on. Let me remove dielectric and get you a conductor. Okay. I get you a conductor. This is a conductor to me. This conductor is being divided. This side is rho 1. This side is rho 2. Same current I flow through both the segments. The current will flow through the segment I. This length is L1. This length is L2. It's a conductor now. What is your take on the interface? Will there be any charge accumulation at the interface?
So there are different resistivities.
Yeah. One is rho 1, the other is rho 2. The current remains.
The current is the same, and the physical dimensions, except for the length, is also the same.
Correct.
Right. So I mean, if we use the formula J is equal to sigma E, well, we know J is constant. I mean, that's constant, right? So the electric fields in them must be different, because the rows are different. Consequently, the sigmas are different. So the electric fields must be different.
Correct.
But still, the current is flowing at the same rate. But that wouldn't be affected if there's some stationary charge. I don't know.
No, try it out. Deliberation, of course, you are going right. Absolutely right. As yet, you are perfect. As of present, you are going in the correct direction. I won't ask you to digress. What you said, to accept in total, yes, electric field left should be different from electric field right.
Yes, sir, but how would you take that to formulate a comment on any possible charge buildup at the interface?
You can. That's the reason it's being introduced here. That's the reason I began with flux.
Yes, sir.
That's the reason I began with flux. You want charge. Take a pillbox.
Okay.
Yeah,
okay. I just thought about that. All right. Oh, it's an electric field. Okay, I got it. Electric field's different.
Solve it.
Right, okay.
Got it? Then solve it. Solve it on your own. Take a pillbox.
Yes. All right. So there must be some charge there then.
Of course, it's not to be.
Yeah, the existence of charge is mandated by the fact that the electric fields are different.
Yes. If this is E1 this side, I write E1 minus E2, that the other side, into the area of the pillbox, the cross-sectional area, let us say delta S.
Yes, sir.
Whereas it's different E1 from E2, we ought to have Q enclosed by the pillbox.
Yes, sir.
You get from here? Q enclosed by epsilon naught, right? Yeah.
Yes, sir. All right.
Now it's all about what E can be replaced to. I should be Q. Let's say Q is being asked and given to you V. What it is operated on, V voltage it is operated on. Right? You can write V, E, we can relate them. We are assuming E to be constant, E1 to be constant, E2 to be constant.
Yes, sir.
We can write in terms of voltage E is equal to I, we can use V is equal to IR.
Yes.
And V by L1 is equal to E. V is equal to IR, help me.
Yes, sir.
IIT plus R is what is given to you. R is rho L1 or rho 1. So rho 1 L1 by area capital A, correct here?
Yes.
Minus I rho 2 L2 by A. Now this is what to us? IR, correct?
Yes, sir. So why did we take minus?
Where is that? Because one is entering, the other is leaving, right?
Okay, we're still computing flux, all right.
One it enters, E2 it leaves.
Yes, all right. Okay.
For one case, E dot ds will be positive, the other negative.
Yes, sir.
Okay, so I, V is equal to, and then I should divide by length, correct?
We're computing voltage, right? Okay. Wait.
V is equal to IR, right?
Wait. E is
V is equal to IR, R is rho L by A, correct?
Yes, sir. We have to divide by L1. Okay, I get it.
So here it will be divided by L1, here it will be divided by L2. What is this to us? Is equal to sigma by epsilon naught, correct?
Yes, sir.
So it's just a notation for Q enclosed by L. Right?
Yes, sir. So you took the area with the other side, and you get sigma. Okay, all right.
Okay, dear?
Yes, sir.
What do we get as the end result? L1 gone, L1 gone. Tell me now.
So you get I by A, rho 1 minus rho 2 is equal to sigma by epsilon naught, send over epsilon naught. That's it. You get I epsilon naught, rho 1 minus rho 2 divided by the area.
Exactly. You have charge, correct?
Yes, sir. Currently do.
Had been rho not equal to rho 1, we have some adjustment, some tweak in our statement, which we unflinchingly do make in class, that there will be no accumulation of charge. Certainly there will be accumulation of charge. There will be charge.
So, but
yes.
I think the point of the law still stands,
yes,
because once the charge has been accumulated, it just stays there, and any charge coming in, once that charge buildup has been stabilized.
Once that charge is being established, it's not that it's a perpetual accumulation, of course, but at the same breath, I cannot say that there is no charge. There will be a charge, and that charge will be unscathed, undeterred throughout the operation. Thereafter, whatever is entering should leave.
Yes.
It will build up in one shot, right? But that one shot should be clarified, be known to us, and how we are getting, we must be aware of it.
Yes, sir.
Okay. As this being done, you're aware of charge. We can do the same over here.
So there, how I mean the dielectrics, right? You can't apply the same logic.
And what I do is, and that was a reason, it was part of the course, introducing I in vector form. We have changed I to J. And what is J to me now? J is a vector quantity, it's current density. So I take a question with two media. current entering the interface with an angle alpha and leaving with an angle beta. Okay? So I take two media, write it down. Let us take two media. Let us take two media. This is the media I'm referring to. This is normal to the medium. This is medium taken. The media angle is, let's say, alpha, and this is beta. What is this angle to represent? How is current density moving? This current density in the first medium, and this is the direction of current density in the second medium.
So it also reflects the direction of the electric field, doesn't it?
It does.
Alright. So
But I'm placing my argument vis-a-vis current density.
yes,
So relate to field, of course, I'll be coming to field. First thing first, current density.
it somehow seems to
Now,
undergo
tell me.
diffraction.
Yeah, this is right.
Okay. Oh, it is?
Certainly it is.
Oh, alright.
And what we can say about current over here, Vasudev, is normal. You know, whatever is entering should leave. Whatever is entering, whatever is normal to the interface should leave. This is to get me one equation.
Yes.
What is the equation? J cos of the angle alpha, or J1 cos of the angle alpha should be equal to J2 cos of the angle beta.
Yes, but why are we saying that applies only to the normal component of current density?
Current is always taken normal. Yeah, it has never been taken other than normal. When we define current, we take which direction of current? We take the direction which is perpendicular to the area, correct? When we define wave or wave intensity, what energy do you take? Perpendicular to the cross-sectional area, correct?
Yes.
The current has always been defined. We define pressure, what force we take, perpendicular to the area. There's a different ballgame altogether that we reduce area to 0. Right?
Yep.
Because pressure is point specific.
Yes, sir.
Current to point specific. That makes the point form, as I was buttressing. It is buttressing my point form to be of greater, much more to lay credence, of greater import than V is equal to IR per se.
Yes.
Okay, so current density I have to take normal to the interface. What will I write? J1 cos of the angle alpha should be equal to J2 cos of the angle beta, correct?
Yes, sir.
One more equation, which is what, Vasudev? You're aware of direction of field where? At the interface. Field is not in any direction other than normal to be taken. Particularly in tangential direction, field must nullify, should get annulled. In the direction tangential, can we have field tangential to surface? No. Which direction is the field? We have studied sigma divided by twice epsilon naught or epsilon naught. Can you recollect?
Yes, sir, but that was in the static condition.
That was in which condition? That was for conductor, dear.
Yes, sir,
Conductor just
a conductor
yeah.
in a static condition, right? Once it has
Okay.
once it had stabilized its charge configuration, then there would be no charge moving across its surface. That's why we said the electric field is always normal. But in this case, there's active charge flowing. So can we make the same argument?
That same potential, how can you assign E to it, dear? Go to the mood. How did we get that? We didn't get because the conductor was not to see flow of current. We got because the conductor was at same potential, right? Yeah.
Yes.
How is this an odd to it? Here also the surfaces ought to be at one potential. It cannot have varying potential, correct?
So why can't it have a varying potential? I still don't get that.
We are taking from one medium to the other medium, yeah.
Yes, sir.
How can a surface be at different potential? One surface.
So what's the special thing about a surface that makes it equipotential? Uh,
I want to introduce a surface to it, right? Which has seen stabilization of charge.
okay.
There is no accumulation of charge. There is no furthering to the accumulation. It's being done. Now, why will there be no furthering to accumulation? Why is not taking charge anymore? At being at different potential here, it would have accepted charge, right?
Yeah, okay.
Charge will flow through it, correct?
Yes, sir.
Through the surface, as we are coming from dV is equal to E dot dr, and dV here is 0. I am not, mind you, please don't appropriate words to me. I didn't say that electric field will remain. Electric field will be different, but net electric field on the surface will be 0. On surface, field will be directed only and only tangential. It cannot be in direction, sorry, only and only normal. It cannot be in direction tangential. Tangential field is not allowed. If you allow tangential field, what will happen? Remember what did I tell you in fluid mechanics? There cannot be any force tangential to surface. The moment you will take force tangential to surface, what will happen? Surface will not be stable.
Yes.
Here the surface is stable on what parameter? On charge parameter, correct?
Yes.
We can't say that there will be a field in this direction. I will get current also in this direction here if there is a field or potential difference in this direction.
Yes, sir. But that charge would flow on the surface. Essentially, it would remain on the surface if you.
So I'll get current.
Yes, sir. But like the charge remains on the surface.
Charge remains on surface, but where you're getting charge here? The one which is flowing on the surface, some quantity remain. How are we getting current flow? Which potential difference is maintaining that current flow? I have not applied potential difference. I'm applying potential difference from here to here.
Yes, sir.
From here to here.
So just one second. Can you tell me what direction the potential difference in, or rather, can you just draw the electric field vector? I think that would simplify things a great deal.
Let me get you a case here. This is cylinder. Okay. I apply potential difference between these 2 points.
Yes, sir.
How will, according to you, current flow? Is it obvious from left to right?
Yes.
Okay. Now I ask you on the surface of cylinder. What will you say about the surface of cylinder? Inner surface or outer surface? Aren't they at same potential?
Yes, sir, they are.
If not, what will happen? You obviously know. Current will flow in this direction as well. I'm discounting on it. I'm not taking current flowing in this direction, not in the radially outward direction. Why? Because that is the direction of potential applied. Potential is getting its field this way, and I field in this direction, and I'll take current in commensurate, in consonance with field. If I change the potential now, let's say, what I do next, I take it this way, and then I ask you, okay, tell me, how will that
So would you mind
flow?
drawing it elsewhere? I can't see it.
Yes, sure, dear. This is now the case, inner, outer, and then I ask, Okay, this is at higher potential, this is at lower potential. This is how we are applying potential difference. How will the current flow now?
It won't be an equipotential anymore.
Radially.
Yes, sir. Okay, so let me just summarize what I understood so far. So
Right.
if we take any surface that's perpendicular to the electric field, it must be an equipotential surface, right? I mean that
Yeah.
yeah, okay, that's pretty obvious. But the currents you have drawn there, they wouldn't be flowing in that manner if the electric field was from down to up, would it?
If you
So
get electric field in this direction, then there will be a flow of current maintained in this direction as well.
yes, so in the original diagram you drawn with the current density entering at alpha and leaving at beta, where's the electric field in direction there?
Perpendicular.
So then how is
It
the
cannot be tangential.
yes, isn't it okay? So the electric field is going from down to up. How is the current moving in another direction than the electric field? Isn't J is equal to epsilon E? So it would be
Yes.
scaled version of E.
Because you don't have the same electric field here. This electric field, the tangential, will be annulled, I told you, by the other tangential electric field. This is having E1, this is having E2.
Okay.
It's not same.
Yes, sir.
So the electric field component in the tangential direction, because of one medium, will get nullified, neutralized by the other medium.
So could you draw it? Kind of having a hard time visualizing it.
Okay,
So could you draw those electric fields getting
I'll
cancelled at the
write the
interface?
question for you. See, tell me. You tell me. What will the electric field due to this J? Are you aware of it? You know rho, you know sigma?
Yes, sir.
So
J
what
basic.
do you write? Yeah.
J
So
basic.
J E by rho. Correct? J is equal to E by rho. Can we say?
So J is equal to
J
E
is equal
by
to
rho. Yes, 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 sure.
or E by right, where rho is resistivity, right?
Yes, sir.
Right. I asked you, tell me Vasudev, what will be the component in the horizontal direction? You say the component of E in the horizontal direction, what will it be? Resistivity multiplied with J in which direction? Horizontal direction, correct?
Yes, sir.
What do you get? Rho J
J
sine
sine
of the
alpha.
angle alpha
Yes, sir.
or going to distinguish rho, correct?
Yes, sir.
Got it here?
Yes, sir.
And right? In the other form as well, I'll come to that. And that should be equal to, this should be equal to, tell me what? Rho 2, J2 into sine of the angle, what I've taken beta. So sine of the angle beta.
Yes, sir. Aren't they in the same direction though?
Yeah, minus sine equal to, that is what I said. This minus this, vectorially when you are adding or subtracting, should be equated to 0. They should be equal. If they are in the same direction, we have to mention over here that they should not be in same, they should get nullified.
Yes, sir. But the way you've drawn it, both components will be going to the right. So if you add them, they don't go to 0.
Okay. They won't go to 0. Make a distinction over here that they should not be in the same direction. It's my figment of imagination that I began with, correct? There will be many alpha, beta. It depends on what is alpha, what is beta.
Yes, sir.
Okay, alpha, beta I have not mentioned over here that they ought to be acute angles.
Okay. So beta could be all the way at the other side. So
It should be, it ought to be. It ought to be.
yes, sir. So if alpha is coming this way, then beta, though, if you're measuring it, well, from that it should be negative, right? It should be that way.
Yes.
All right.
Okay.
Yes.
And then from there, you'll get relation.
Yes, sir.
Now I come to the question which is in Ayurveda, which will be solving these are the concept placed over here. Can you take that question?
Yes, sir.
The same figure, alpha, beta, all being given to you. They have given you tan alpha, tan beta as well. That'll help you get to the answer to the question. Okay? A question to you, write it down quickly. If you have, then there's no need to write. I think everyone, you must be having time, just letting you know the question number.
So just a second, I'll get the book.
Get the book.
I don't know what version they're printing, but all these books still say printed in the Soviet Union.
The time it was unilaterally to be decided by CBS, I do had much of know on what is placed at which point. As Aryant and the other did, I don't know, somehow sneak their way in. Much has. Nevertheless, I read the question to you. Please see that the language, the body of the question
So could you tell me the
has
question
not.
number?
This is 18.
Question
Starting.
18.
1-8.
1-8 is in, I mean, you must have got the numbering
First
wrong. Sir?
Electrodynamics.
Electrodynamics.
Why don't you write it down? Write it down. Let's write it down. Demonstrate that. Write down. Not much.
Alright.
Demonstrate that.
So illustrate that.
Demonstrate.
Demonstrate.
Demonstrate that law of refraction. Demonstrate that law of refraction of direct current lines at the boundary between two conducting media. At the boundary between two conducting media has the form tan alpha 2 divided by tan alpha 1, tan alpha 2 upon tan alpha 1 is equal to sigma 2 upon sigma 1, where sigma 1 and sigma 2 are conductivities of the media, and alpha 1 and alpha 2 are the angles between current lines and normal to the boundary surface. So everything out here remain except for alpha beta right here.
Yes, sir.
One is alpha 1 and the other is alpha 2. So for the case, J1, J2 remain. J1, J2 remain. Alpha 2, alpha 1 accordingly you can mark.
Yes.
Lower will be alpha 1 if lower is J1. Accordingly the upper one will be alpha 2. Correct?
Yes, sir.
Okay, can you demonstrate this relation here? Not much now left. You're aware of what to do here. Just equating E, nothing much.
Yes, sir. I think got it.
Okay. So what will be E1? E1, which component we require? That also is to be checked here.
Yes, sir.
Okay, so what will be? Tell me.
So you get.
I require tangential component, correct?
Yes, sir.
From this vector relation, I get J by sigma. I have the general equation, but with J, I have to take J in the direction tangential, correct?
Yes, sir.
So J sine of the angle, can you mark alpha 1?
Yes, sir.
J1 rather,
Yes, sir.
divided by what we should write, sigma 1
Sigma 1.
equal to J2 sine of the angle alpha 2 divided by sigma 2, right here.
Yes, sir.
Now current in the direction normal to the boundary will remain, correct?
Cool.
What we get from there? From there we get J1 cos of the angle alpha should be equal to J2 cos of the angle alpha 1, let us say alpha 1 to take it. Alpha 2, right? Yeah.
Yes, sir.
And the third one. Can we prove the third one then based on these two, which is what was to be proven?
You just divide them. You do get that equation.
Are you clear on this?
Yes, sir. So I just wanted to confirm this one last time. If alpha is positive and you're measuring angles in a certain direction, beta has to be negative, right?
Right.
They have to be of opposite sign.
Yeah.
Okay.
Else they will not cancel first.
Yeah.
Okay. Now one more term, which is right now. Let us take a dielectric. Let us take a dielectric with X part of it. With X part of it within the plates of capacitor. With X part of it within the plates of capacitor. Very important, this one. Again, there is heck of a lot of confusion on how do we get it, how to rather interpret it. So this is a dielectric with dielectric constant K, and this to me is plate of capacitor. This dimension is A to me, this dimension is B to me, plates being rectangular in shape. Okay, dear?
So what are the plates here?
These are the plates,
Okay, alright.
rectangular in shape and between dielectric, but dielectric has occupied as of now only portion X. Fine?
Yes, okay, so it's like partially slided in.
Partially within it.
Yes, sir.
Part of it is within it. And what I do next is I connect it with a battery. What does the battery do? Will maintain potential difference. Battery of EMF or terminal potential difference P. Arrangement known, experimentation now is to be done, some observation to be made, and those observations are to go a long way in the understanding out here. So tell me, Vasudev, how many capacitors do we have? You will say there are two.
So two parallel capacitors, one with a
Two
dielectric and
parallel
one without.
capacitors. So C equivalent, how do they act? C1 plus C2. C equivalent is what to us? C1 plus C2, right?
Yes, sir.
Okay. Now C1 is what to us? C1 is equal to, or any C is A epsilon naught by D, we know. A over here will be small a into x, epsilon naught as it is by D. Please do check and confirm on the same.
Yes, sir.
Okay. C2, dear. C2, tell me about C2. This is C2.
So
What will be A over here?
A times B minus X times
B minus X. B minus X. into A. So K will not be in this case seen, but K will be seen in the first case because it is with the dielectric, correct?
Yes, okay, already writing epsilon naught. Yeah, I get it. Okay. Yes.
Total C equivalent how much? Tell me, add them and get me a few terms common. A epsilon naught by D, check what I'm writing is correct or not. B minus 1 into X plus something. Just check once.
Yes, sir.
Uh, A epsilon by D I'm taking out.
Since we get the kappa x plus b minus x.
B minus
So you get k. Sorry, you get
K.
x kappa
A
minus
minus
one
1.
plus b.
A minus 1 into X plus B, right?
Yes, sir. Yeah, right. That was.
This is C equivalent, correct?
Yes, sir.
Now this dielectric going to, and there is only one reason which can justify what I'm to make as a statement now. And I'm making a very important statement. So much so that I did mention underscore it. The statement which I'm into making is dielectric will be pulled in. Why will it be pulled in? Owing to the fact that there is fringing of electric field lines.
Yes,
And
sir.
those fringing are to get it a catapult effect. So it will be pushed in, it will be sucked in.
Yes, sir.
Let it move by certain distance, Vasudev, very small distance, delta x. Very small. What will that delta x bring as change in capacitance? So delta x will get you, delta c will be a constant, epsilon constant, d constant, bracket open, k minus
Could you write
1
it, sir?
into delta x, right?
So I can't exactly see that.
Okay, no issues. I'll write up. K a epsilon naught by d k minus 1 into delta x. This is what you will get as delta c. How? It is x now. After some time, this will be x plus delta x, correct?
Yes, sir. Okay, the b's cancel out, right? Okay, I get it.
Got
Yes,
it? So this is what you will be left with, correct?
yes. Basically just differentiating it. Dx.
This is the correct. So delta C is this to me. This is the change in capacitance owing to movement of dielectric by what distance? By distance delta x.
Yes, sir.
So capacitance got changed. Potential cannot change. Why? It is being maintained.
So the capacitor will draw in more charge from the battery.
Correct. Charge will change. More of the charge will be drawn from that. How much charge? How much additional charge will be drawn from battery next? What will be additional work done by battery? What will be additional work done? For that, I have to write what is work done by battery. You are aware of. Work done by battery is equal to what to us? Q into E, correct here?
Yes, sir.
Work done by battery is Q into E. And what is Q? Q is equal to C into E, right?
Q
Q is equal to what to us? C into E, right?
Yes, sir. Yes, sir. Q is-
Capacitance formula.
Yes, sir.
So work done by battery can be marked as CE squared, correct?
Yes, sir.
I was looking for additional work done. So additional work done by battery will be delta W, delta C into E square. Agreed?
Yes, sir. So that's transferred to the dielectric as kinetic energy.
Yes, this is the energy additional, but I didn't get that. You said that this is being stored in the dielectric. Let us see what dielectric is storing. What dielectric stores will depend on which formula? Half C E squared. So additional energy that the dielectric is storing, owing to change in capacitance, will be half delta C into E square. Half of it, correct?
Yes, sir. So, oh, okay, I think I get it. The electric field, the energy is also stored in the electric field, right? So the electric field is getting diminished progressively. So that will also consume some energy, right?
Energy over here cannot be equated firstly, because this is a field which is non-conservative. You have a source here. So battery is doing work.
Yes, sir.
Work done by battery is being used as A. Change in potential, that you know. B. Energy associated with dielectric. Now you may say, let us take mass of dielectric 0. What energy you are referring to? I'll say you are still to refer to energy. Why? Because you are pulling the dielectric in. And it will not be pulled in slowly. If you want to pull it slowly, then you can absorb yourself of kinetic energy, correct? But for it to be pulled in slowly, you require a person over here to hold it. Are you getting it?
Yes, sir.
So what can we say? Work done by battery is going in A, increasing potential energy, certainly which potential? Electrostatic potential energy, and also which is doing work against applied force. I will have to hold it. This will be pulled in by a force, correct? If I'm not holding, it will go in with kinetic energy. I don't want kinetic energy to feature. What I have to do, I have to hold it. So this force will do work against applied force, correct?
Yes, sir.
What then we get now as a very important relation? Delta CE square. This is work done by battery, which is equal to half delta CE square. What is this to us? Increasing potential energy, electrostatic potential energy. Plus what? Plus F into delta X. You may ask why I'm taking F to be constant. I'll tell you that you are aware of that. It is not impulsive for sure.
So what did you say?
Force is not impulsive. This force is not impulsive. What I'm referring to this force.
Yes,
It
sir.
is non-impulsive force, fine.
Yes, sir.
And I have taken delta X to be very small.
Yes, okay, I get it. It has to change continuously, and that means over a small interval can take into
Right. Right. Now, what is the magic out here is to be checked. This is delta U twice.
Yes.
This is delta U, right? I can mark as delta U, yes or no? Change in potential energy.
So could you come again? I couldn't hear you.
This is delta U, change in potential energy, right?
Yes, sir.
This is twice of delta U, correct?
Yes, sir.
What do you get? Twice of delta U is equal to delta U plus F delta X, right?
Yes, sir.
Then from here, delta U by delta X is equal to F. There is no negative sign. F is what from here is delta U by delta X. It is not minus of delta U by delta X. Why? Because this force is certainly not conservative in nature. When or how can we make it conservative? By removing cell. Remove the cell now, this becomes zero. Work done by cell 0, remove cell. What is this then to us? 0, correct?
Yes, sir.
In that case, what we will get is
You'll get
F
negative.
is equal to minus of delta U by delta. Those will come from a different understanding there. This is equation wise. There V will not remain same, Q will remain same.
Yes, sir. So basically, the battery is doing irreversible work when it's pushing charges onto the two plates.
Yes, it is a source to you. How can you use force to be conservative when there is a source of swing? It cannot be.
Yes, sir.
Got it? And when we are to remove battery, Q will be constant, and from there we get delta U by delta. We write Q square by 2C. C will be written the same, and then we'll differentiate to get force.
Yes, sir.
Okay? So we'll study in detail about it. We'll study, but before getting a closure to this, I get your question. There is a spring. Let's say disturbed by a certain amount, very small. Will it execute simple harmonic motion?
So that depends on the nature of the. It's not connected to a battery, yeah.
Connected to battery.
It is connected to battery. Okay. I don't think it will.
That depends on force that you are getting. What is force? Can you write delta U by delta X? Can you tell me force?
So, but SHM only works when the force is conservative, right?
Correct, yeah. But if the force comes out to be constant, how does it matter if it is conservative or not conservative? If there is a force which is constant in direction of SHM.
Yes, but my point is, isn't force a function of X here?
It is a function of X, dear, but it is not one force which is to govern its motion. One is the spring force and the other is the force which we just now spoke about.
Yes, sir.
Spring force certainly will help. But what was the force that we spoke about? Is that force constant? If that force is constant, it will execute simple harmonic motion.
So what force are you talking about?
Force here which we wrote, delta U by delta X.
Yes, so that's a function of X, right?
That is what I'm asking. Please find it out.
Oh, so
you have delta U, you have delta X. Find it out, yeah. Okay. Delta U is there. That is delta U, right? Half delta C square.
Yes, sir.
Right, delta C. Delta C I have gotten you, dear. Delta X gone.
Okay. Yes, sir. So the force
is
constant?
Out to be a constant.
Okay. Yeah, then it's constant. Then yeah, SHM. You will get SHM.
And was the battery not connected?
So, it wouldn't be SHM, would it?
In that case, we will prove that force depends on X.
Yes.
And if force depends on X, there it will not execute simple harmonic motion.
Yes.
The other questions amalgamation there. We'll be seeing more of it. Thank you, dear.
Yes, sir. I just wanted to ask you, you've sent me a message about some kind of engagement with a colleague of yours on Monday?
Yeah, there's a fellow for 28. You will have to be free on that day because I have asked him. But he's also to get a result in top this time as well. He has been getting results, but this time 113 out of 120 is what he's doing. But he has asked me not to get it. And secondly, the spur of the moment happened for it. And secondly, he is exceptional in his field. We worked together long back, about 20 years ago, 2 decades. She will be able to let you know on how to prepare for that examination. You will also ask him questions which you have kept for long.
Yes.
And he will throw some light on those questions. Then not all can be taken, but whichever the area of ambiguity, you can ask the question based on it.
Sure, sir. I will. Thank you.
Okay, thank you.